Things become more concrete when you start talking about cases where you have a real question, like how well can I predict a certain thing with these variables? So for prediction, the only thing that you care about is the prediction error. That's it. So some kind of measure that compares your observed outcome of the people to the prediction for them and says, here's how good you're doing, right? So the clear thing to do is to pick the model that gives you the lowest prediction error, however you define prediction error. So that could be mean squared error, for example. But as we talked about a couple weeks ago, there's different ways to define what you mean by prediction error. So we'll use MSE here because it's very common. So if you recall, it's the observed outcome minus the prediction squared, and then the sample average of that. The problem is that this is actually not the MSE that we care about. So I kind of lied to you for a couple of weeks. This is the sample MSE. Why don't we care about the sample MSE? Because in practice, we want to be making predictions for people in the future, right? We train some kind of predictive model, and then somebody, let's say you're trying to predict who's going to get a heart attack while they're in the ICU or something like that. Well, you train it, and then you want to go in the future to an ICU, and for somebody who's admitted, you want to say, hey, this person's going to have a heart attack, we should do something about it. Why is it useless to have a prediction for the people who are already in your data set? Because they already had heart attacks or they didn't, right? So who cares how well you can predict whether or not somebody who already had a heart attack, if they were going to have a heart attack or not? It's totally pointless. So we don't actually care about the sample MSE. These are the wrong people. We care about, and this is, by the way, sample MSE also is called the training error. This is the kind of more like machine learning lingo for this. So I'll use both interchangeably. Who do we care about? We care about the population. We care about the people who we're going to use this model to predict for in the future, right? So we want to know, how well can we predict for people who are outside of the sample, who we have not yet observed, right? And that's the same thing. It's just instead of averaging over the sample, we want to average over the entire population. The problem is that actually if some of you may think, why can't we just use training error as an estimate of population error? Aren't these two things the same, except who you're averaging over? But, by the central limit theorem, this thing should be, or not even the central limit theorem, just take the expectation of this, pass it through. It should be this, right? So this should be kind of an unbiased estimate of this, because this is a sum of these IID terms. X and Y are IID, right? So what's the problem? It turns out, no, this does not work. And the reason is that the terms in this sum are not IID. Yes, Y and X are IID across different people, but this mu hat is not IID, right? What I mean is that this mu hat, the regression function that you chose this by looking at all of the rows in the data set, right? So this guy has seen all of the rows in the data set, and now you're plugging it in to these different terms in this estimator and kind of assuming that those different terms are IID, but they aren't, because this has seen everything already. So the central limit theorem doesn't actually apply here. This training error is not a good estimate of the population error. And in fact, you can see this in simulation. So what I'm doing here is I am sampling from some data generating process. If you want to see exactly, it's in the notes for the slide down here. But I'm sampling from some data generating process which has X and Y. I'm regressing Y onto X. I'm calculating the training error by predicting on that data and subtracting off the observed outcome and squaring it. So that's the training error. And I'm calculating the population error by using this population data set that I generated outside of this code. So I have the data generating process. So I just sampled like 1 million people from that data generating process, which are different than the sample that I'm using to train the model, right? So here I can actually calculate the population error. That's not possible in practice, right? But for the purposes of demonstrating that these two things are different, I can play God and show you here. And then I'm plotting I repeat this 1,000 times, and I'm plotting the distribution of the training error and the population error that I'm getting. And you see that the training error is very much underrepresenting the actual population error. So that's bad, right? My models, if I just look at the training error, I think I can predict a lot better than I actually can. And the reason that happens is because it's like, if you think of the data as kind of like the homework assignment, right? So if you think of the prediction model as trying to learn some function, trying to learn some material, right? And the data that you show it is kind of like the homework that you're saying, okay, do these homework problems, try to predict the outcome given these predictors, and you do this for these n rows of data. These are all the homework problems that you get to see. And then you say, okay, now here's the test to see if you've actually learned anything. And the test is the exact same homework problems. That's not a good test, because someone can just memorize the answer to those homework problems without actually understanding anything, right? There's no generalization. And that's why, in any course, in this course and other courses, there's never you're going to get a test that's exactly the same with the exact same numbers and everything as you got on the homework assignment. So it's the same thing here. You can't test your model using the exact same data that you used to train the model, that it used to learn in the first place. So it's, this prediction function was chosen specifically to make this training error as small as possible, right? Of all the possible prediction models, it's actually a model selection problem, right? It's very similar to what we were doing before, right? Like, so if the assumption is that you already have this prediction function, like God came and gave it to you, then yes, these terms are IID. Everything is good. You can use central limit theorem. This will be a good approximation of the population error. But really, you're ignoring the fact that you did this model fitting. And the model fitting is a lot like model selection, because you're choosing between different values of the coefficients. Is it beta 1 equals 5? Is it beta 1 equals 10? Is it beta 1 equals negative 10? Right? So that model fitting is a lot like model selection. It basically is the same thing. And you're ignoring that happened when you're calculating the training error. So you need to take that into account. And the way that you do it is exactly the same as if you're trying to combat the model selection bias, which is that you split your data into, in this case, what we're going to call the training sample and the testing sample. So the training sample you use to fit the model, and then you have the model, that's done. And then you evaluate that model using the test sample. So here, this is like the homework questions, and then these are the test questions, right? That's what's called test sample. And then you get the error estimate is based on how well this model is predicting the outcomes for these people, which it never saw before, because they didn't go into the fitting of the model. So like I said, this test set mimics a fair test or a fair exam that has new questions that are different than what was on the homework or covered in class. And this thing is unbiased. So how do you do this? So if you have your data, here I'm drawing it from a data drawing process, but you could, if in practice you just had a data set, it's the same thing. Here I'm just taking the first 50 rows as the training data and the last 50 rows as the test data. So I just split it in half in terms of rows. Very simple. I train the model using just the training data. Okay, so notice there's no test data here. And then I can calculate my errors. So the training error, I calculate based on the training data set. The test error, I do the same thing, I just put the test data here. But notice, again, the test data never went into this LM call. So this M has never seen this test data before. And then for reference, I also calculate the population error again. This is based on some really, really large population data set that I generated outside of this code. And you can see here the distribution of errors. Training error is low, but it's artificial, right? The population error is around here at like 0.3. And you can see that the testing error is unbiased, right? So the testing error is actually capturing. It's more spread out than the population error is, right? But it's unbiased. On average, you're getting the right answer. Why is it more spread out? Because we only have 50 data points in the test, right? Whereas the population data is like 1 million people or something, right? And we just don't know how well this model is doing. We don't have that degree of accuracy, right? If we're only giving 50 test questions. What I mean is that, like, let's say you have a class and you're trying to say who gets an A, who gets a B, and you only have a test with 2 questions on it. There's only 2 questions. So basically there's only 3 grades that people can get. It's either an A, like 100%, a 50%, or a 0%. And that's just not a very like nuanced picture of how much somebody understands, right? Maybe somebody understands 70% of the material, but if you have that test, they're only going to get 50% because it's not 100. So it kind of doesn't give you the best picture of where people are at. If you have a test with 10,000 questions, you're going to get a very, very nuanced idea of how well somebody understands the material. Of course, that's ridiculous, but that's basically what's going on here, right? Is the population data is a test with 10,000 questions. So you're getting a very clear, precise notion of how well this model is doing. The test set, it's a smaller, maybe it's like, think of it as a quiz or something, right? Here it's a small test set, so you're going to get kind of more spread out. It's not a perfect judgment, but it is at least unbiased, unlike the training error, which is systematically lower. So the message here is that you should use test error to select models, not training error. You can use this test error to just compare, right? So we're going back to what we were talking about here. The idea is we want to know, should we be doing this or should we be doing this? If you just looked at training error, training MSE to compare them, it would actually always pick the more complicated thing. But if you use test error, the answer may be different. So let's see what happens here. So we're being asked to compare these two models that are fit in terms of training and test MSE, and then make these scatter plots. Great. Okay, so Tidy Models is a nice package. I think we talked about it briefly maybe in the linear regression mechanics section, but it has a lot of different kind of machine learning stuff in it. And we'll talk more about it later, but one of the things that I'm going to use from it right now is this initial split function. So this is just going to split this data set into training and testing. Of course, I should load it. Okay, so now if I do split, you're going to see it just prints out training, testing, total. So how do I get out just the training data? You do training split. So you see this has 1,000 rows, and then testing. This has 300 rows. So I just use the default. You can tell it, I think, how much to put into training and testing with this proportion argument. So by default, it's 3/4, so it puts 3/4 into training and 1/4 into testing. We'll talk more later about what the impacts of where you put your data are. But generally speaking, we already talked a little bit about testing. The more testing data you have, the more accurate you'll be able to judge the performance of your model. The more training data you have, the better model you may get. And so there's actually a bit of a trade-off between having a better model and being able to tell you have a better model. Okay, so what are we doing here? We've split up our data. We're training 2 different models, M1 and M2. And these models are different. So here M2 is simpler. So if I print them out, you'll see what I mean. So M2, so these are different spline models. You can go back to 2 weeks ago, we introduced splines. Basically, these are fitting, instead of doing a linear regression, you're fitting, well, here degree equals 2. So these are like kind of piecewise quadratic fits of the data. And you're kind of gluing 4 parabolas together, basically. That's what this is saying. Glue 4 parabolas together in some way to fit the data. So this, and you end up with these four different coefficients here. The other model is more complicated because here I'm saying, sorry, here we go, glue 30 parabolas together. So I'm getting a lot more coefficients. So this first model is much more complicated and the second model is simpler, relatively speaking. So let's evaluate the training and test mean squared errors. So I can do M1, let's say predict. So these are the residuals. And then here's the mean squared error, and then here's the root mean squared error. Oh yeah, it's called charges. Okay. So this is the root mean squared error for model 1. Let's training error, root mean squared training error, root mean squared training error for model 2. So if we compare these, this is better. This is the smaller number. So this is suggesting we should go with model 1, the more complex model. It has lower training error, right? But let's compare the test error. Okay, for model 1, and then for model 2. So for test error, this number is lower than that number. The simpler model has less test error, even though it has more training error. But as we know, the test error is actually the thing that's more reflective of the population error. And so what this suggests is that the simpler model is actually the one that we should go to if we want better predictive performance. So now I'm asking, okay, make a scatter plot of charges versus age and overlay the predictions. So what, yeah, the models that we're doing here are predicting charges from age. So let's actually just plot what's happening. We can do, let's put the whole data set into ggplot. And then so these are the predictions from the first model. Okay. So this is the okay. So this is the predictions from the first model, and then these are the predictions from the second model. So remember, the first one is the more complex model. This is the simpler model. So what you should be seeing here is that the more complicated we make the model, the more kind of wiggly that line is going to be. And that line is actually trying to chase, this line is kind of trying to chase these, whatever the training data are. So in this case, it looks like randomly, maybe there was more training data down here than up here, and up here, there's kind of more training data up here, but that was just an artifact of what data we got in the training set. If we redo the split, let's re-split it, retrain, and now, those wiggles are going to be slightly different, right? So it's kind of chasing the data a little bit too much and resulting in a fit that is actually not very predictive when you put new data in of what's going to happen. It's overly sensitive to the data that you're putting in. So let's talk a little bit about that. It turns out that there is a sweet spot in model complexity that minimizes population error. So here I'm fitting degree 1 splines, which is a fancy way of saying I'm gluing together some k number of lines, and that I'm saying how can I glue together k lines to get the best possible regression. So here if I have 3 pieces I can glue together, throw that in the algorithm, it's going to say I'm going to put a break here and a break here, and then the slope like that and like that and like that, and that's the best I can do. And this is optimizing over all places where you could put the breaks and the slopes of all these different lines. This is the best that you get. If you say instead, I'm gonna tell you can break the line in 10 places, so you get 11 segments, then this is the fit you get. And here, by the way, the dotted gray line is the true conditional mean for this data generating process, which in reality you don't know, right? But that's the fit that you get with 11. df is degrees of freedom. In this case, that corresponds with just how many line segments you get. And I could go crazy. I could say, well, I'm going to give you 90 different line segments that you can glue together to try to predict these points. And what you see here is that it's really just connect the dots, right? By the way, there's 100 data points. So here I can basically connect the dots. If you have 90 line segments, you can actually hit like 90 of the points, right? And you just leave like 10 out, right? So it's just connect the dots between the data, basically. But is that a good prediction of this gray line, right? And the answer is no, this one is better, right? This pink line is actually more reflective of the dotted gray line than this one is. This one has more error, right? And so this, what over here we say this is overfitting and this is underfitting. So underfitting means your model is not flexible enough to capture the true relationship. Overfitting means your model is so complex that you're chasing the data rather than capturing any more generalizable relationship. So when you do model selection with a test set, you're going to end up, well, we'll see what happens. Let's just plot, right? Well, let's first plot the training error and the generalization error. So what's the training error over here? That's for df equals 3. Well, you just add up all these residuals, right? And they're all pretty big. So all these data are pretty far from this red line. So it's going to be pretty big training error. Over here, more moderate. And then over here, the training error is nearly 0 because we're actually almost interpolating all of the data, right? So for this data point, this data point, this data point, there's 0 training error. We're actually hitting it, right? So very small training error over here. And that's what we see. So here I've kind of redone this, varying the degrees of freedom between 0 and 70. And you can see that the training error is decreasing, always decreasing, right? Because you're just interpolating more and more of the data. However, the population error goes down at first, so kind of reflecting the fact that from here to here, we're improving, right? But then after a point, we start worsening by making the model more complex. So the population error first is decreasing and then starts increasing. And then, basically the difference between here and here, this is the optimism of the training error, right? The population error is higher than the training error in general. So if we could see the population error directly, which in practice we can't, right? But if we could see it, we would know that really the best place to stop would be 21 degrees of freedom, right? Because this is the minimum error in the population. So we would just pick this as our model, right? The one that has 21 degrees of freedom, not 20, not 40, not 5. But if we were using the training error, we would keep going forever, right? We would say 100 degrees of freedom, as many as possible. As we saw, the test error is reflective of the population error. So here, if I plot the test error that I get from basically splitting these data in half, using half of them to train this model, and then the other half to compute the error, the test error is reflective of the population error, and it has the same minimum. And so if I use test error, I'm going to get the right model. But unfortunately, the problem with using a test set is that you need to split off some of your data. And like I said, there's a trade-off between having a good model and being able to evaluate that model well. And so if I'm putting a lot of the data into the test set, then I'm having less data I can use to train the model, and that's not great. I'd say in 2024, if you have hundreds of observations, it's worth it to split off some for the test set, like 20%, something like that, fine. But if you're in 1972 and, you're collecting data sets that are, 20 samples or something like that, this was a problem. You couldn't just use a test set. And so people had creative ideas. And the idea is, instead of using a test set, why don't we judge based on the training error plus some kind of penalty of complexity? So I know the training error is going to keep going down forever, right? But the problem is that, okay, I know that as I add complexity to my model, so in this case, it's, the complexity is measured by how many of these line segments I can glue together. I know that that should be increasing the population error at some point. And so why don't I just add some penalty? I look at the training error, because that is reflective up to a point, but then I'm going to add some penalty to this that says maybe my penalty is dependent on the number of degrees of freedom or the model complexity, so that after a while this starts going up. So in this case, the measure of complexity for a linear regression is basically just the number of coefficients that you're fitting. And so here what I'm plotting, this thing called AIC, I'll tell you what that is in a second. It's just the training error. It's just this curve plus some constant times whatever number is down here. So I've just basically put a line like that, and then I've added that line to this thing. And so here you can see it's kind of curving down, but there's always some kind of difference here. This difference here is proportional to how far along we are on the x-axis. That's all that's here in the black. But what you can see is that this black curve actually, it's not reflective of the population error up here, but down here it actually has a very similar minimum. And so if we use this thing, that will actually also select the right model. So AIC, this thing is called the Akiake Information Criterion. And there's also a thing called BIC, Bayesian Information Criteria. It's a similar idea. It's a variant on this. This really doesn't matter what the difference is to you. Shouldn't care. I just want you to know what it is. It's a kind of cheap estimate of population error. It's good for small n, but it's less generally useful than looking at test error. So in 2024, test error is kind of the way to go. Unless you have very small data, in which case, yeah, okay, AIC, fine, BIC, whatever. You can use these things. You just need to recognize them because they do come up sometimes. So for example, when you're doing this forward regression in R, it turns out that one of the things that it uses to judge whether it's going to include a term or not is this AIC. And yeah, it's just a measure of like population error, predictive accuracy.